adopting green energy. And today we have the pleasure of speaking with Roberto Gambini on the reverse enthalpy methodology for evaluating risk and uncertainty in geothermal projects. So risk and uncertainty is a concept that cannot be divorced from geothermal development. And having a good understanding of risk and uncertainty is critical to making sound decisions on investment and development. The methodology is an innovative approach inspired by best practice from the hydrocarbon industry, but then it's specifically tailored to the dynamics of the geothermal industry. Roberto Gambini is a visiting professor of geology of energy transition at the University of Chieti-Pescara in Italy. He is a highly experienced technical and commercial manager with almost 4 decades of international experience in the geothermal and upstream energy sectors. He has held a senior leadership role in Enel Green Power, where he was head of the global geothermal technological line, and he was responsible for Enel's worldwide geothermal portfolio. In this role, he gained extensive expertise across all stages of geothermal project development and contributed to advancing technological and strategic innovations within the sector. So we're very much looking forward to this webinar. And for everyone in the audience, feel free to type in your questions. There should be a questions tab somewhere in the webinar panel. Type in your questions there anytime, and we'll get to them after the talk. And so, Roberto, welcome. The floor is yours.
Thank you, Carlo. Thank you for inviting me and the opportunity to talk about the methodology that we have developed. So this methodology is the result basically of probably 5, 6, 7 years. So is will be clear why we call the reverse enthalpy methodology when I'm going in the detail in the methodology. We have recently published one paper. You can see here the link, and the QR code is an open access paper, so you can download as you like. We have also presented this methodology in several congresses. We are arranging this webinar to disseminate this methodology as well, in this webinar. We are also arranging some course we have done in conjunction with the ROSE subsurface assessment. We put it together 2 different type of course. One day course dedicated to the focus to the managers, decision maker, authorities. So people that needs to know about this methodology, they are using this methodology to take the decision for their business. And a 3 days course for geoscientists, engineers, that they need to produce this number, the evaluation. We have 2 events planned, one in Zagreb and the other in Izmir. The one in Zagreb is nearly sold out. I think probably there is just 1 seat left. We still have more availability for Izmir. We are also producing a software. We have already the beta version. This software allowed to do in a quick way the implementation of this methodology. We are also producing a textbook, much in a large version of our paper, and our intention is to give an open access also this textbook. So I hope beginning next year, so in January, next January, will be available for downloads. For any information, you can contact me or Peter Pestman from ROSE Associate Subsurface Assessment. Okay, why quantify risk uncertainties is really critical. Obviously, we know is for decision-making process, comparing one project to another. So, yeah, it's obviously important. Even for risk mitigation system, how to implement in in a right way. But I wanted to really focus on project financing. Everybody is well known in geothermal business community, of course, that the risk, as you can see from the diagram on the left, the risk at the beginning and exploration phase is very high, and decrease with the de-risking, more activity, the drilling the well, and so on. On the other side, the costs are increasing, going ahead with the development of the project, but be able to quantify in a proper way with the standardized system really help in financing the project. To cover this risk, who is putting the equity money at the beginning exploration phase, obviously they are looking for higher return, while at the end, the de-risking period after the drilling the well, before the starting the development, really the risk decreased quite a lot, and the weighted average capital costs are much lower. So we start in the beginning maximum 20%, and we go down to 8% as a minimum. So be able to de-risk, so to quantify the risk in the different stage is absolutely critical for the success of this project. Our system is based on the principle oil and gas. Why? Because they are clear, well established, has been around for 150 years, and is already in the DNA of the financial community. When I speak with them, with the people running equity funds and so on, every time they ask me, but there is a way to quantify, like in the oil and gas, is probable, proven, possible resource. Also in the geothermal, what is the pause of this project? So the concept, risk and uncertainties of the oil and gas is something that everybody knows, well established, consolidated. So our challenge started really, can we apply the same concept, easy, understandable, easy to implement it, even to the geothermal? So before to start to see risk uncertainties assessment in the geothermal, we need really to understand which kind of concept, oil and gas, are we referring. So basically there are three key concepts. Probability geological success is really the chance that we drill a well and in the traps we find hydrocarbon. It's a binary result. We can find hydrocarbon or water or no reservoir, dry. So failure is a really success, failure. And typical way to represent is with decision tree, with the pause probability that we drill, we find hydrocarbon, and 1 minus pause, the risk is a probability of a failure. This is the first concept that we can take from the oil and gas. The other is uncertainties. Uncertainty, what it is. After I found, okay, in the traps there is hydrocarbon, how much I've found? I've found the equivalent a cup of tea, or I found the huge Goar field in Saudi Arabia. These are the two extremes. And how I represent the uncertainties. Uncertainty is typically represented by a probability distribution function. I like mostly the way to represent it with the cumulative distribution function. From this point onwards, you will see just cumulative distribution function, because are really the most one that they really provide information to us. The third point is the probability distribution function of any field discovery. By definition, will have one part that will represent volumes too small to be commercial, and one instead that one section that will be large enough to be commercial. So the idea that we have a minimum commercial field size, so is the smallest field, they still have NPV. NPV, net present value, in simple terms is we make money. With an NPV positive means we make money out of this. So we have a minimum commercial field size that define really is a threshold. Above these volumes, we make money. Below this volume, we lose money. How we calculate what we call the probability of success? Simply we plot on a commercial, on a cumulative distribution function, this volume, and we read the probability. P sub C is the probability to find at least this minimum commercial field size. So is the probability to find, to make money out of this project. In this case, in the diagram that I reproduce on the right is 65%. So corresponded to P65, that is really 65% probability to find the minimum commercial field size or higher. That means I make money. And so how we represent it? So the formula is very simple. Is probability of success is probability to find some hydrocarbon multiplied probability to find enough to make money. Very simple formula. But how we translate for a geothermal? Let's start to focus on P sub G, on geological success. As we said in oil and gas, we drill it, the traps is filled of oil or is empty. Binary. And there is still a parameter like that in the geothermal. Definitely, yes. We may have the geology wrong. We drill it as something in our geological model is wrong, doesn't work, and we drill it, we don't find what we wanted. So that is a probability that our interpretation, our geological work is done correctly. We are predicting correctly all the geothermal elements to be there. But there is something more that is not in the oil and gas. In the IFC report 2013, there are a lot of really good points. One thing that they really saw that is in the geothermal, a dry well is really a rarity. Almost all well produces something. So it's not black and white, but something was producing. And in a certain way, when we drill deep in the earth, we will find some heat. So what they introduce? The concept that not enough flow rate per well deliverability, inadequate well deliverability, and inadequate reservoir temperature. About a suitable geothermal fluid chemistry, correctly in the report they speak a lot, and in the paper that I mentioned you will find it. I'm not going in detail on this aspect because it will be too long for a half an hour presentation. So you can read how to treat this extra point in the paper, but I'm not going to talk about this. Will be really definitely too much. So going back to the other 2 points, well deliverability and the temperature, what they really said that successful is defined, exceed a defined threshold. Exceed the defined threshold, we can easily quantify with a cumulative distribution curves. So if we are evaluating one project and we have a design for a plant, this case 60 degrees was a district heating, was also supported by a large heat pump. So the reference temperature for our design is 60 degrees. We can calculate the probability of having 60 degrees or higher is what we need for the development that we are considering. We can plot on the cumulative distribution function of the temperature, and we can read the probability of having this temperature of higher. How we produce the temperature distribution, cumulative distribution function? In the usual way that we produce this curve in the oil and gas. So we use every data that we have, fluid wells, geothermometers, every heat flow map, everything we have, we calibrate these curves and we generate this type of cumulative distribution. That is really a critical point, how we generate this, and is mostly the focus of the course that we are giving on these topics. So in this way, using this cumulative distribution function, and knowing from the design of our plant the temperature that we needed, we can calculate this probability. This probability, in any case, is a probability that depends on the type of the development. Will be not really valid for any kind of project development, but is specific at the design, the type that we have in mind, how we want to develop the field. PGM, we introduce M that stands for model, geological model, so general frame is correct or not. Instead, is totally independent by the chosen development plan. So depends only by the geology. So one term is independent and rely on geology, based on geology. The other is strongly linked to the type of the development. For example, will be much higher for a power plant than for a district, the temperature, because we know that we need a less, higher temperature. For the simplicity, I'm just assuming a single phase geothermal fluid, so it's correct to talk about the temperature. In reality, if we are multi-phase, I should talk about enthalpy. But to keep simple the presentation, I'm just talking about the temperature. Keep in mind that I'm referring to a single phase fluid. At this P sub G, composed by these 12 elements, is still missing the flow rate. The flow rate we are capturing the risk of enough flow rate in P sub C, the commercial chance of success. So now let's focus on these parameters. These parameters in the oil and gas is easy, relatively easy, because the parameters that best really describe the monetary value of a project is volume recovered hydrocarbon, the amount of the barrels, million barrels, so that we can produce at the end of the life of the field. One field with 10 million of barrels will be less profitable than a field with 100 million barrels. There is no ambiguity. Of course, there are other parameters, but the overall volume of recoverable hydrocarbon is the single parameters that at the end is so much important that all the other are not so important, not so critical. But what about in the geothermal, which is the best parameters that represent the monetary value of a project? Okay, this is a typical textbook of equation, the power, thermal power, and so on. At the end is depend from the flow rate delta T between the inflow and outflow of the water after for a binary, for example, after the heat exchanger. So the delta T of the generated give the heat to the system. So that is definitely the key parameter. So in theory, we could use this parameter to represent the project, but as we can see from these diagrams, dependent by the temperature. Having a lower temperature, we need much higher flow rate. Look in the graph on the bottom left. Okay, we should convert the thermal in electricity and is the diagram on the top right. But also the capex, they are depending by the temperature. So if we have a higher temperature, the capex for a power plant at 20 megawatt will be much less than one at 100 degrees. So higher temperature will cost less than a lower temperature, the same size of a plant. So these thermal power parameters still has some ambiguity, cannot be used unless we know also the temperature. So standalone as a single parameters cannot be used to represent the monetary value of a project. So at the end, we have 4 different parameters: temperature, well reliability, drilling cost, and facility cost. The first one is captured in what I already explained. I took the probability, the threshold probability, the temperature. So I have not to worry about because it's treated in the P sub G. The well reliability, drilling cost, of course, they are connected because the well reliability, if very high, I need less well to feed a certain kind of, for a certain size power plant or district heating, whatever. And therefore, I will need less well and I will spend less. So these two are connected. So, but even though we are still having too many parameters, so I need to eliminate one. And how we can do? We can do making some assumption. So this is option 1, option 2 of a REM. Option 1, we take as assumption that we take a priori the facilities as an input. Option 2, as we will see, the number of well is taken as given as a priori decision. Why? In reality, why taking as a priori decision? Because most of the time we decide in the real life the size of the power plant is decided not for technical reason, but for other business reasons. Sometimes there are grid limitations, like we cannot do a very large power plant. Sometimes we adopt a phase development by different phase with a pilot, main development, and additional development in 3 different stages to de-risk the subsequent phase. In other case, we decide, like some company they do, to have all the power plant exactly the same capacity, to have the spare party, the critical spare party, saving some money. So that is for more than one plant. So sometimes we take this decision. In any case, we can readjust the plant capacity in an iterative way until we are happy. Why we call the reverse enthalpy methodology? Because, for example, in option 1, we have a priori determination of the capacity, and we, in typical reverse engineering process, we calculate all the other parameters starting from the power plant capacity. So option 1, as I said, we establish a priori a certain kind of capacity, a type of development. In this way, the only variable became the well reliability. Well reliability will affect the drilling cost. So drilling cost will be the critical, because the facilities will capex will become an input at the, because we have decided a priori the type and the capacity of these facilities. So at the end, we can calculate the drilling cost that make NPV equal 0. And this drilling cost, we said the well durability. So the starting point is the well durability. Better the well will produce, and I will need less well. So better is the well, and the drilling cost will be less, and I will make more money. NPV will be larger. So very simple. So going through, I can calculate, for example, this is a case of a 20 megawatt binary at assuming a temperature of fluid 180 degrees. So I can calculate how many total number of wells I needed. So, and this is varying according the capability of the well to perform better or worse. More well if the wells produce less, less well if I produce my well producing very well. So at the end, I can convert in drilling cost, and I will calculate the drilling cost that make my NPV equal 0. And that corresponds, like in the oil and gas minimum commercial field size, I can calculate the probability of achieving this drilling cost or lower in this case, and this will be my P sub C, and that is option 1. Option 2 instead is we are working on the number of wells. Most of the case we have the not a lot of space to drill well. We may have a national park. We may have a restriction because there are village, city, and so on. So at the end, I've been involved in a project where at the end we had just a 2 well pad. So we needed just a 2 area where we could drill the wells. So at the end, that can be a constraint. Of course, within my license area, I cannot drill outside my license area. So having my drilling cost as an input a priori, I can work exactly like in option 1, but calculating on base of well deliverability to calculate the minimum capacity, power plant capacity or facility capacity, and make my NPV equal to 0. Of course, reducing or the power plant, I reduce the capex, but also I reduce the revenue. So I will arrive at a point that the smallest lower will be NPV negative. So that is my equivalent to minimum commercial field size for the oil and gas. And I can plot this according to the well deliverability and calculate my P sub C, my commercial chance of success. In this case, is correspond to a 15 megawatt binary power plant. So working and assuming a priori option 1 facilities, option 2 number of well drilling cost, I can in an iterative way calculate and estimate my probability of achieving P sub C equal probability that makes my project NPV 0. So if I succeed this value, I make money. If I below, I lose money. And that will correspond to my probability commercial success. So how to apply? As I said, project approval, option 1, option 2, our recommendation is doing both. Why? Because they give you a different point of view of your project, help you in optimize your project from a point of view really risk optimization. Option 1 tell you how many dry wells, for example, you can drill before to make negative. And it's a concept in the oil and gas well known, it's called the dry hole tolerance. So how many times you can make a well wrong well before your NPV became negative. That is very important, and I've seen some decision makers be very happy to when we were really providing this kind of information. Option 2 instead give you the perspective and really how big you can do your maximum, your power plant, or minimum your power plant before you start losing money. And that is another point of view. So working together in an iterative way, you can really better understand how the different factors they are interacting each other, and you can really optimize at the optimum way your risk profile that you want to take it. So obviously need a little bit to be trained, because we are using normally the cumulative, the probability distribution factor from Monte Carlo. Here instead we are using to calculate the risk, to estimate the risk. So need to be trained a little bit how we do it. So that is what we are teaching in the course. Development for specific probability, that I have a slide on this. Sometimes after at the end we have optimized everything we linked, someone say, yeah, but specifically this project, regardless the commercial factor, what is the probability success of this particular development? So I'm referring particularly temperature reference and to achieve a particular minimum level of flow rate. In this case, is not dependent by the economic evaluation, but is dependent completely by the development scheme, type, capacity that we choose. In this case, we call the probability technical success, and is given by geology right, minimum temperature achievement, and minimum well-derivability of the design. And the formula is pretty simple. So far, we have discussed the probability threshold for well-derivability just for using P sub C. In this case, instead, is just used for understanding the project specifically. So EMV, we need a little bit to the discussion. So we need for EMV to capture the entire outcome, the entire course, we need the 3 points, P90, P10, P50. So these 3 values are obtained using the option 2. That is what we already have seen, but in this case, we calculate the P90, the P50, and the P10 cases of the power plant. So is the power plant generate the P90, power plant capacity generate P50 and the P10. We need to understand that the limitation is not truly Monte Carlo, is based on well-derivability distribution function, and is referring always on a well-established number of wells. So the number of wells is not changing, and the temperature is the one that is captured by the probability threshold of a temperature that is part of the P sub G. So therefore is not directly comparable with the oil and gas case. In this case, by the way, as you can see on the P90 case, the volume, the power plant of the P90 case is smaller than the minimum commercial, therefore has an NPV negative. So, but in the way that this EMV is calculated, we need to capture this negative event. Using this approach, we can build the usual way, the decision tree with the EMV calculator. EMV, if you like, we can call it risk-adjusted NPV. So it's an NPV that is taking account also of the chance of success. This obviously, I'm showing this, but it's part of the course. We are discussing in detail this part. So, another way that we can use, and just mentioning, in what I already mentioned, the phased project development. So, and there is a typical way to de-risk a region is having a pilot, main development, and further extension. In this case, the decision tree is much more complex because we have a several stage decision. We have drilled the first exploration well, develop the pilot, develop the main, develop the extension. It's a simple repeated 3 times, but this approach allowed to calculate the overall evaluation, the full development phase with the 3 stages. So in summary, P-sub-G capture the geology, the chance of having the geology right. Is my geology, my model right? Yes or no? The threshold, the temperature, is capture the chance of having the fluid temperature equal or higher than the threshold value. This threshold value is the number that the facilities engineer is using to design the plant. And finally, the P-sub-C option 1 or 2 is capture the chance of having the well deliverability good enough to make the NPV equal 0. So a final consideration, why this we push for this methodology, because it's simple at the end, is strongly rooted on in geology and engineering, but at the end provide the value that is independent from the geology engineering part. Is a value, is a probability of achieving NPV, or if you like, a probability of making money. So at the end is a parameter that's really what the investor they want. The investor at the end, they wanted to know what is the probability to make money or lose money. And that at the end, the POS, how is calculated, even though is strongly based on geology engineering, is provide this value. How is the chance to make money? That is really what they wanted. So at the end, this is basically the end of my presentation. I'm ready to answer your question. So I was strictly in time, 40 minutes. Fantastic.
Roberto, thank you very much for that presentation. It's a very interesting approach to evaluating risk and uncertainty, in that you start with the commercial considerations first before you go to, and that's the starting point for the modeling and for the evaluation. And so I guess that's very interesting, considering how a lot of companies do them, by starting with the more technical aspects, right?
Good. So is any question specifically?
Okay, for the audience, just feel free to type in your questions and we'll get to them. But let's start with a couple that are a bit more basic.
Yeah.
So in your method, there are like 2 options for a priori assumptions. Based on your, say, experience or conversations with geothermal developers and operators, what is the most common scenario? What is the priori assumption for most scenarios, for most of the real world scenarios?
The real world scenarios I have seen at the facilities. So we started at the option 1 for a long period. Option 1 was the only option in reality, because at the end, you know, the power plant, yes, definitely the geology tell you the capacity. In reality, what we are estimating is the aquifer, the capability of the aquifer to produce power or heating. So that is linked to area, but no one really commit for the P50 case. Normally the people, they take really stage by stage, step by step approach. So first the pilot, main development, further development. So to start directly with the P50 case that is typical for the oil and gas business is, for my experience, at the end, when you, because at the end of the day, geothermal compared to the oil and gas is a much more risk adverse than oil and gas. So step-by-step facilities is, in my view, could be the more common one.
Yeah, that makes sense. That makes sense for most cases. Say if you have a field with a potential of say 200, 300 megawatts, you always start with, I don't know, 30 or 50.
Yeah, exactly. Yeah.
Okay then. How does the model, is there a way for the model to to present different capex scenarios? Say if you encounter acidic fluids, and of course you have to increase capex, or if you have to do any sort of stimulation. Is there a way for sorry, go ahead.
Sure, definitely. In this way, we generate a different scenario. At the end, we combine the different scenario with the typical decision tree approach, putting the different probability of occurring one scenario compared to the other. But at the end, what my experience tell me, really at the end, the several scenario, at the end, most of them will be so marginal economic or no economic, then some of those scenario can be included in the failure scenario. So at the end, what normally we suggest to have this, first of all, divergent phase, where you analyze, you try to look for different out-of-box thinking, so on, a different type of scenario to have as many as you can generate. But after you have a convergence phase, where you are starting to eliminate some of those scenarios to converge on really what make the difference in terms of money, what does really matter. And based on my experience, I was portfolio manager in OMV and in Shell, and one thing is really avoid to have too many scenarios, because to have this unmanageable decision tree is a nightmare. So try to keep it simple as much as possible. But definitely the scenario, different scenario and decision tree approach can help you in consider different capex and so on.
Okay, picking up from that line of questioning, and also it's fairly expected that we go to this topic, but how can the method be applied to say EGS projects, considering as well the uncertainty of stimulation and establishing connectivity?
Definitely, yeah. Now that is a really good question. In the paper that you can download, there is one specific, we treated these topics. For EGS is needed to have an extra cumulative distribution function, and is the volume rocks that is being affected by fracking. So because we know that having one single fracture that even produce a lot of fluid is not enough, because we need to extract heat from a decent volume of rocks. So we need to include these uncertainties, that is how much rocks we manage to frack with our fracking job, and be able to extract heat from a reasonable amount of volume. So it's something particular, so and slightly different from the conventional approach. But this methodology is definitely possible to apply also for EGS.
Okay then, but I suppose for those who are really interested, they would have to look into your paper to see exactly how the method can be applied for EGS.
Yeah, and also in the textbook, though, we are expanding the paper in the textbook. Why? Okay, because that was very long. deliver a process in producing this paper. And every time we wrote too much for a 20, 30 page paper. And at the end, we had to remove a lot of parts. So we are putting together the part that we had removed to keep it the number of the page in a reasonable number. And you know, this risk uncertainty is really an it's really a subject that so extensive, so with a lot of implication, really is needed to have 150 pages at least to cover every single aspect. So hopefully in the book that we are preparing, and by the way, we, as already I mentioned, will be open access. So we are not restricted, we are not selling, but you will be able to download. We are going to cover in more detail all these aspects, and as well in the course. Also in the course we are giving, the 3-day course, we are going to cover this aspect as well.
Okay, let's talk about that course maybe a bit later. I also have questions about it, but let's go to some of the questions from the audience. How does the methodology change between heat and or power applications?
No, it doesn't change. The principle is the same. Is absolutely the same. Is no change at all. Is apply exactly, and is apply every time so that you need to, you have uncertainties in the flow rate and uncertainties in the temperature is exactly the same.
Exactly. Okay, is there any specialized software needed or tools to be able to do this kind of methodology?
Yeah, that is a good question. We are producing a software. It's no need a specific software, but a software can help you in doing a quicker way. What we are producing, we have already a beta version of software. This software works for the CapEx, for the drilling cost, for the gathering system with some these generic curves. So we have basically generic cursor works that is varying the cost. For example, the drilling cost is varying the cost of the drilling according to the depth for a certain particular specific geology. So keeping the geology constant, the cost of the well will vary mainly due to the different TD. So we have these curves that represent the different costs for different different depth. The same power plant for different flow rate, different temperature, and so on. Gathering system, different distance, and so on. So this software allowed you to change quickly the number of wells, flow rate per well, cost of capex, or whatever, in a very easy way, and come out with the P sub C, MPV equals 0. And so the software is not needed, but the one that we are producing will help in making this calculation for screening and for a quick evaluation very, very easy. Of course, needed to generate these curves, but a facilities engineer or a drilling manager can produce these curves very easily. Yeah, and for specific type of the development, for specific type of geology, and so on. We have a beta version, and we hope to be able to make available this software by the end of the year or beginning next year in January. In few months, a couple of months.
Okay, so there's a lot to look forward to. You have the book, you have the software, and also have the courses. Okay, so if there was, say, a developer interested in taking these courses of yours, would you recommend that? What kind of role should the person have on the company for to make the best use of this knowledge of this course?
Okay, the 3 days definitely is for people that are involved in producing the PSAP-G, the PSAP-C, the evaluation. So geoscientists, but also facilities engineer in geothermal, we know very well that is much more integrated. The power plant, the reservoir is just an unicum, is one thing that works together. So, and the communication, we cannot really, any business is wrong to work in 4 stage in a separate really, but any kind of business, you need integration. In geothermal, this is even more true. So it's definitely integration, multidisciplinary approach is vital. So I strongly recommend it. Everybody that is involved in technical side for the geothermal project, from the exploration to the development facilities, all to definitely, and also for the classroom is definitely, we have seen that when the based on my experience, when you have a really multidisciplinary group, it's definitely also the way that the people are working for the exercise all together are much better, and they integrate much better. So is higher level. So everybody involved is highly recommendable. We have also 1-day course for decision maker and authorities. This is really for the people, is designed for the people that they don't need to know enough to produce this number, but the people that need to know what this number means to be used, to be able to take the right decision. So understanding this number, understanding the good and the limitation, and be able to apply correctly. But at the moment, we don't have a schedule, any 1-day course for manager and authorities. Will be probably, we are thinking to have one in London in the near future, but we don't have yet anything scheduled. If someone is interested, obviously we can really to see and to arrange it as is needed. So we are open to to have one of those if
So
it's
if you're doing
requested.
that, then you will of course help promote it. And so if anyone's interested, then you just watch out for any announcements in the future. Okay, here's another interesting question. Whenever there's a new, say, methodology or modeling method, it's always very interesting to try to apply it retroactively to existing projects in the past that have been developed or have failed. I imagine this might be something that you've done as an exercise. So, are there like any examples that you've worked on say, projects, existing fields where you've applied this methodology?
Yes, we applied in the past. Obviously, there are some confidentiality stuff that we cannot disclose. The example we put in the paper is an example of, let's say, more an academic study, is in the here in Italy. So we couldn't really show. If someone is interested to apply this methodology on their field and is available to make these studies evaluation available for the textbook, for example, or for the course, etc. Yeah, please contact me. We will be more than happy to apply. Of course, that would be within a frame of cooperation. So will be no charge for this if there is a possibility to publish it. So if you have one case that you like to do it and you are not you don't have a confidentiality constraint, we will be more than happy to work on this project, on this evaluation, and publish this evaluation as example in the book.
I think it could be a very good opportunity for joint research projects, say between
absolutely.
you and the people who are working in the geothermal fields.
Yeah.
Okay then. The paper briefly mentions that you have you've made some effort to align it with existing frameworks when it comes to risk assessment. Are there plans to try to standardize this across the whole geothermal industry? And what do you think will be the challenges for that?
Yeah, definitely. Yes. We had today, this morning, a discussion with one company that is very good, top class in reservoir modeling. The idea is to generate a third type of course that is integrating reservoir geothermal modeling with our methodology. Our methodology, in reality, is a way to treat the data to come out with a P sub C, P sub G, commercial chance of success, job, blah, blah, blah. In the paper, there is one section that is speaking about integration of reservoir modeling. In this area, we think we need to, we have some idea, we have a strong idea how to do it. We have done already in some instance this, but to have a standard, we have not yet published anything with a standardized workflow how to integrate this methodology with reservoir modeling, because we need some case history that we can publish. Therefore, when we will have, we like to publish something or to make available something about the workflow and how to integrate reservoir modeling, numerical modeling with this our methodology.
Okay, then. I mean, I'm looking forward to that. Like to make it more robust using real life data. I think that real world data. I think that'd be a very good way to move forward with the project.
Absolutely.
Yeah. Okay then. We're almost running out of time, so maybe just a last question. Uh, with your experience in looking into geothermal projects, like how companies nowadays do their risk evaluation, what would you recommend are the say best practices or new methodologies, new methods that they can start trying to do to improve their risk evaluation and uncertainty assessment?
Yeah, I think the best way is really to have the analyze. Okay, the first thing is really how we approach the project, the risk uncertainties. Risk uncertainties, there is how we look all the aspect is is not just a single answer, but there are several answers that we need to put all together to really to understand the risk of the project and the weakness, the strength, and so on. So it's a more philosophical approach. My recommendation is, first of all, we need never to take shortcut. We need definitely to do all the homework in detail, step by step, in understanding in detail all the aspects as much we can. And once we have done it, really to analyze under every kind of a point of view. For this reason, I always recommend option 1 and option 2, because give 2 different point of view. At the end, when really we are happy, we don't need to present to the top management all the story, but we need to select the 3 cases that represent really best risk uncertainties our project, and present to them in a simplified way, in a such way that they are able to take the right business decision. So that is definitely a workflow that we recommend and a philosophic approach. Really.
Yeah, and I agree. At the end, it's really about condensing all of this mostly technical information into something that is more easily understood and also in a commercial language, because ultimately that is what management needs and the investors need.
Absolutely. What we need always to recall, and is what I really I always, is the mantra I always repeat to my student: geothermal is not a science. Geothermal is a commercial activity that is rooted in science, is using the science, but itself is not a science, is a commercial activity, is make money producing power and heat. So therefore we need to convert technical information, geological information, engineering information in business decision. A business decision need to generate NPV positive. So that is our focus, and that is the reason why we have put together this particular methodology, because really our focus is into making money. That is really should be always our focus, definitely.
Okay, then that's a very good way of looking at things. And on that note, thank you very much, Roberto. Thank you as well to
Very
the
good.
attendees who showed up, and for those who
Thank
asked questions. For those who want more information, their paper is open. You can like check out the link or just search for them. It's very easy. And also they have a series of courses in Zagreb and Izmir, right? If we'll make an announcement on the website, on our website, so
Okay.
everyone who's interested can sign up. This recording will be uploaded to our YouTube channel like in maybe 1 week as well, for those who missed the first part of it. And watch out for another Focus on Geothermal webinar in 2 weeks. Thank you again, Roberto.
Thank you to you, Carlo. Really, I appreciate it. Thanks a lot. Thank you.
Thank you, everyone. Have a good weekend.
Bye. Bye. Ciao, grazie.
Bye.
Bye.